Okay, I want to show you how to calculate branch current given the RMS and phase voltage measurements of the branch elements between the connecting nodes on either side of the element. And you may have taken some data where you may have VA RMS and VB RMS, and then some phase, we'll say angle of A minus angle of B. You've collected this maybe in the lab with the DSO or something. And what you want to do is you want to find what is the current, what is the magnitude of this current and the phase of this current. So this is what I want to kind of walk through. So in principle, we just need to calculate the phasor voltage VZ as VA minus VB. Right? That's not hard to do if VA and VB are in Cartesian coordinates, but of course they're not, so that's where our work will be. But let's go ahead and finish this out. If we have VZ, then we simply need to take VZ and divide it by the impedance Z to find our IZ. Okay, so let's assume that VA is equal to some VA RMS and some angle theta A. Okay, and if we could write this in Cartesian coordinates as VA RMS times cosine of theta A plus J times VA RMS times sine of theta A. We could do the same thing for VB. All right, and so now when we write VZ, we can simply do the differencing in Cartesian form. Right? So we have VA RMS cosine A minus VB RMS cosine theta B. Right? That's going to be our real part, plus J times VA RMS sine theta A minus VB RMS sine of theta B. And this would be in Cartesian form, and of course we want it ultimately in polar form because we want to report what is the RMS current. So this here will be the real part of VZ, and this would be the imaginary part of VZ. So we could write VZ as equal to VZ RMS and then some angle of VZ, where VZ RMS is simply going to be the square root of the real VZ plus the imaginary VZ, quantity squared, and where the angle of VZ is the arctan of the imaginary part of VZ divided by the real part of VZ. Okay, so recapping, if you are starting off with data here, a table where you've measured VA RMS, VB RMS, and the angle between the two, we could say that this angle, we could clarify first by saying, well, angle A is 0. That's my reference signal that I was using. So therefore, angle B is going to be equal to, I'll just call this phase. So it's going to be equal to minus phase, right? Whatever the scope returns. So we have the angle of VA, the angle of VB, and the RMS of VA and VB. So we have these four values here. So we can, from this, we can calculate the real part of VZ by simply using the RMS values of VA and VB along with the angles of VA and VB. We can do the same for calculating the imaginary part of VZ. And this can all be done if you're working in a spreadsheet. You can just add additional columns to say this is the real part of VZ, this is the imaginary part of VZ, or you could collapse it all into one column and do all your calculation in one fell swoop, where you would report on the RMS of VZ and then the angle of VZ. That's up to you. But either way, it shouldn't be very difficult to be able to compute the current going in, or the current flowing IZ as a function of measured node voltages VA and VB. As a final note, okay, so final note, if your problem is as follows, okay, where let's say we have VA here and you have VB here, and I've got some R, okay, and what I'm really asked to do, let me say I'll call this VG, okay, what I'm really trying to do is find out what is the Z equivalent looking into this network. And it just so happens that my network starts off with a resistance R. And I have measured, this is my ground here, okay, so VA is the voltage between that node A, and ground, and then VB is the voltage between that node B and ground. And I have those two voltages, RMS of each and the phase between them, and I know what this resistance is, whatever, let's say it's 10 kilo ohms. So what I'm really trying to do is calculate the impedance Z equivalent. All right. Well, what I need to know there is I need to know the voltage, VG, which presumably that's something that actually is equal to VA. It's the same thing. Okay. And then I need to know what is the current going in. So I'll call this IG. Right. Well, IG can simply be computed by looking at, if my voltage here, voltage across that resistance is VR, I can calculate IG by doing VR over the resistance, right? And how do I get VR? Well, we just calculated VR. That was our VZ, right, for the general case. So likely if you're watching this, you're actually trying to solve this problem here. You're trying to take experimental data and determine what is the impedance looking into this one-port network. And you have voltages VA and VB in terms of RMS values and a phase difference between the two. And between nodes A and B, you have a resistance, 10K, 20K, whatever, 1 ohm. You have something. And so you need to calculate the current entering that one port so that ultimately you can calculate the equivalent impedance looking into the network. So hopefully, with all that said now, it's clear that you can calculate the impedance looking into this network by simply having the RMS values of node A and node B and the phase difference between node A and node B voltage.